Hello, my name is Evgeny. Today we will talk about the Heta components and how they describe a dynamic system. We will also talk about the mathematical expressions and assignments. As you know, the straightforward way to describe the evolution of a system is to write ODEs. In other words, in terms of variable, parameter, event, and so on. You can solve it starting from some initial values using numerical methods or sometimes analytically. This approach looks simple, but it's not simple from the modeler's point of view. Any minor updates to the model result in hard work for modifying the structure of the ODE code. Everything will become worse if the dimension of a system is high. That's why, in many cases, the modelers prefer working in other terms, species, reactions, and other ones. For example, SBML, antimony, and Heta formats deal with the process description approach in opposite to the ODE-based approach. The approach allows writing the model in a compact form and updating it simpler. The process description model code is usually more natural for human understanding in comparison to ODEs. If you want to simulate the created model, the compiler will create and run ODEs on the fly, based on the predefined translation rules. The components in Heta are parts of a model written in process description format, and they describe a dynamic system. Components and terms in Heta are most like SBML, but they have some differences. There are different types of components in Heta, which we call classes. To create a new component in a Heta platform, we must use insert action. The component of a particular class has some required and optional attributes which we call properties. Classes inherit properties from other classes, and all components inherit from the component class. We see here the UML diagram with all Heta classes. For example, we see that species inherits from record class. This means that the components of the species class has the properties isAmount, compartment, as well as the assignments, units, property, and other ones. Today we will work with classes Const, record, and process. Const is the most simple component. In the shortened form you just write ID, set class, and num property, which is always a number. A constant is a part of a dynamic system that cannot be changed during simulation. This is the input of simulations. The constant component should be used when we describe the numerical parameters, conditions, for example, rate constant or dissociation constant. Another component class is the record. This is maybe the most important component. We will pay more attention on it. In general, the record describes the value that may change in time, depending on the assignments and the processes. Records describe the dynamic characteristics and can be used as simulation results or auxiliary variables used internally. The value of a record can be updated explicitly by the assignment property. The assignment must be a dictionary. The keys display when the assignment runs. This is the assignment scope. The value is a mathematical expression for the assignment calculation, or just a number. As you see, there are several assignment scopes here. The first and the second ones are the predefined scopes, start and ODE. The start assignment runs once at the initial step, before solving the system. Another predefined scope is ODE, and the value of a component is recalculated at each time point, for example, at each point of solution. When we use this assignment, we will describe the explicit rule for calculation of the value. If you use both start and ODE, the start will be omitted because ODE starts at each point, including the initial one. And what about the other scopes? Users can define other scopes when they create events, but we're going to talk about it on the other lessons. Another way of changing the record value is to bind it with a process component. But if you want to protect a record from processes, you should set the boundary property as true. Let's see what the process is. The process is the same as the record, but it has the additional actors property. The most simple way of writing the actors is to use the process expression string. It includes references to other records. And this means we establish the rate of increase or decrease for those values taking into account the stoichiometry. Process usually uses the ODE assignment. You see here several examples of process expressions. And now let's see how the components work together. We start from a constant component. I'm creating x0 constant with the value 10. If we run the simulations, we would see that the value does not change. I'll draw it like this. Always 10. Now I want to create two records. Both of them have only start assignment in shortened form, but the first one is assigned by a number, and the second one is assigned by an expression. If we simulated the records, we would see something like this. P1 is assigned by 0.1 at 0 time and does not change for other points. The expression will be calculated based on the values of x0 and p1 at 0 time, assigned to p2 value, and then the value does not change. I would like to say a couple of words about the mathematical expressions. In Heta, you can use the expressions of any size. You can use operators, plus, minus, divide, as well as functions and others. You can find more details in the specification page. The sequence of components declaration is not important for assignments. You can first declare const or record and use it inside the assignments or declare it after. So if you could put the const after the record, this result would be the same. The compiler will order the assignments after loading all components. The only thing to avoid is the cyclic assignment. Now I'm creating another two records. The first one has start assignment. T means here simulation time, which can be used inside expressions. The second component has the same expression, but in ODE scope. Let's see where is the difference. P3 is calculated on 0 time and the value is null. The value does not change. In opposite, P4 recalculates the assignment based on different time points. It increased together with time. Another example. I am creating two records X and Y. If we simulated them, we would see the following picture. Now let's add the process like this. Here, peer 1 is the process that decreases the value of x and increases y. Now let's see what was changed. X was assigned to 10 and then it was decreased by the process. Peer 1 is also a record that is calculated based on ODE assignment at each time point. Now let's try the boundary property. What if we set true for x record? In that case, the process does not play a role. X is not changing. Peer 1 is calculated based on x and also isn't changing. But y is still increased at a constant rate. But what if we remove boundary from x and assign it as a rule? We saw the same results, but there is one difference. X value is recalculated many times. If the expression included, for example, time dependence, it would display changes. But these changes are still not under the process control. To get more practice with process description format, let's create a model. In the scheme you see 2 tanks with water and 3 fluxes changing water volume. The initial volumes are 50 and 10 liters. The first pipe pumps water with a rate of 5 liters per hour from some unknown source. The second pipe transforms water from the first tank to the second one with a rate of 3 liters per hour. The third one is the outflow from the tank to outside. The rates of 2 fluxes are constant, whereas the third one depends on the water column height, like shown by the expression. To calculate the height, we can use the area size, which is 2 square decimeters. We can describe this model using constants, records, and processes. This is not a typical QSP model, but it's a good example for understanding the process description approach. Fine, let's write what we see using the Heta notation. First of all, let's create 2 volumes assigned by the initial value. Then we are describing fluxes as processes because they are changed the water volumes. Flux 1. The rate is constant, but we will write it as ODE type assignment. We must describe actors here. We see it's an influx, so we are not filling up the left part of the expression. On the right side, we just write vol 1. Let's write a similar process for the second pipe. The outflux from vol 1 is equal to the influx of vol 2, so the stoichiometry of the process is 1:1. And finally the process number 3. This process depends on h, which is height of water. The volume depends on volume 2. When volume 2 changes, the h will also change. This means that we should use h as a record. S means area size. Its value doesn't change, so we can include it as a constant. I also want to use named constant instead of a number in flux 3. I want to create Matlab code, so I'm writing the export action. Before we run the simulations, I would like you to show how this model looks in ODE notation. I wrote the equations manually just to show you, but you don't need to write it for simulations. The Heta compiler will do it for you at export step if they are required. If we compare two types of notation, we see that constant became constant parameters, records with ODE scope became rules or parameters depending on other parameters and time. Records inside processes became the ordinary equations with initial values. Now I'm going to run this model in Matlab. Open console, write Heta build as usual. As we can see, there are no errors. Then I'm looking at this directory. I see here the directory Matlab because we set this name in file path property. You see three files inside: model, param and run. We need run m file, which is generated code for simulation in plot. Let's open the directory in the Explorer and double click on run m file. This file is intended for running. Other files include model code and parameter values. The only thing that I want to change is the list of records for output. I need only wall 1 and wall 2. To run the code, just press Ctrl plus Enter and wait for a while. We can see the dynamics of water volumes here. That's all for today. Follow the Heta project site and subscribe to our channel. Thank you for your time. Goodbye.